So a video lesson, if you like, just to try and go through some of the three-phase issues we've just been having, looking at how to identify three-phase sinusoidal wave, how to move it over into a vector diagram, and then understanding what a balanced and an unbalanced system is. So initially we're just going to take a look at how the sinusoidal wave is created and then transfer it over into a vector and then start looking at three-phase and how to balance these systems out. So in front of us now, I've just done a home diagram. Unfortunately, the laptops we've been given are pretty naff for doing any drawing. And it's just the small things in life like the PCs that we use, even though they're shocking as well, they are far better than these little Chromebooks. So the diagram we've just drawn out in front is basically just the generator. So the rotational rotor within inside the generator, we have our two poles, our south and our north poles. And from there, all I've drawn in then is the lines of flux. So this is the magnetic flux between, and as you can see, the most dense, so the flux density is at its peak right in the center of the magnetic fields. So as our generator is traveling then anti-clockwise through this, we can see then where it starts to cut these lines of flux, and then we can start to look at how this transfers over to a sinusoidal wave. So you can see right at the very start, we've placed our 0 degrees. This is just going to be a reference for our vector in a second. And at 0 degrees, it's barely cutting any lines of force. There is no magnetic field being produced into the conductors themselves. Then as it starts to rotate down through, we start cutting far more lines. So the magnetic flux density, the greater the magnetic field, the faster the rotation, and the longer these conductors are, means the greater the actual voltage or the EMF that's going to be produced within this. Then it starts to come down back out of the field at our 180 degrees. Then again, we're not cutting any magnetic lines of flux, and then it travels back through and now up through the cycle. Therefore this is our negative cycle, back to our 270 degrees where we're now cutting negative peak, and then it comes back out of this. So in here, all I've really identified is that we have a couple of things that we look at on a sinusoidal wave, and these are peak. So usually it's done peak to peak, so this is positive peak here to negative peak on the opposite side. We'll also then look at our root mean square, so our RMS value, and again this is measured at 4 points, so we'll come back to this. But RMS is basically the 4 strongest points of magnetic field. If we were just to take it out our peak and our peak, these wouldn't give us a viable field, and I'll again quickly explain in a second. And then our average, and our average is roughly at our 45 degree mark across all fields. So generation of magnetic field. Moving this down to the next stage then, what I'm just going to quickly do first, you can identify at the top of here, we've put our 0 degrees. This is the weakest point, the starting point, if you like, on our generation. So as it gets up to our speed and momentum. So what I am going to do, however, is just turn this then on its side, just so that we can then look at a vector diagram and the sinusoidal wave. So our starting point would now be the 0 degrees. It would then build up to the 90, back down to the 180, and then peak again at 270 and back around to the 0. So hopefully what I could do is just then, my next little drawing from home, if I move this one out of the field, we then come on to our sinusoidal wave. So again, this is our 0 degrees. This is basically the generator we've just looked at. This is the rotational field within, but this is the starting now point of our vector. So we now have our y-axis, positive and negative, and our x-axis, positive and negative. So looking again over at the sinusoidal wave, I've just put on there again our average cycle, our RMS, and then our peak, which drops down again to our 0, our 270 degrees, sorry, 180 degrees, down to our 270 degree peak, and then back to our 0. So all these drawings I have put in a little PDF and put up onto the Google Classroom. So all we've done then basically is now transfer this into a vector. So this is our starting mechanism. As it starts to then start to rotate through these fields, it starts to then move up our sinusoidal wave, and we start to then see the output that we're getting. RMS, however, is the 4 most positive lines of flux that are cut, and RMS is around 120 degrees, so it's just around here at the moment. And I'll show you how this imposes when we have 3 phases put onto this system. But again, looking at the drawing, I have put these on a PDF so you can have a quick look at on Google Classroom, just so you can re-familiarise yourself or go back through this video and then make any notes on there. But that's how we transfer the sinusoidal wave over into a vector. So now we can lose the sinusoidal wave and now concentrate on this vector. We've transferred the sinusoidal onto the vector. What I'm going to do is now move that vector and then basically give it a little bit more information, just as a little bit more guidance. So on here, you can now see that I've put on our 0 degrees on our x-axis, and as we start to travel through, we get our averages around this 45 degree mark, to our RMS value, through to our 90 degree peak. So measured on a sinusoidal wave, peak to peak is our positive and negative cycle. Then we travel round through, so again our average is imposed on there, 180 to negative averages 270 around to 315, back up to 0 degrees. But what we now need to make sure that we're taking from this is our RMS is absolutely key. And again, on a single phase system, we would look at RMS only at the 4 points of RMS. So we would put this into both cycles. So as it goes through the sinusoidal wave, our RMS value, is not only at this point here, but it is also here. It is now also here, and it is also here. So from there, we're now going to then take a look at the RMS factors. So RMS in a vector is now going to look like this. Again, at the moment, this is for a single phase system only. All we put on there is the 4 points of RMS value. What we need to then take a look at is obviously we've looked at single phase and how these points are measured out, so our RMS value. Well, RMS is now taken on a 3-phase system, because looking at our generator, we now have 3 sets of coils. So every time they cut through 3 points of north and south. Therefore, the most efficient, effective way of generating electrical systems or electrical power. What I'm going to show you from here, though, is if we was to take our starting point, so our RMS from each of these. So RMS starts on this point here on our single phase, on our first phase, sorry. Our RMS is then achieved on our second phase at this point, and then our RMS on our third cycle is achieved at this point. These are all measured at 120 degree cycles, so they are basically split into the 3 sets of coils, separated evenly apart, each at 120 degrees to each other. What I've now done is I've transferred the 3-phase RMS, so the first initial RMS, onto a vector diagram. And from that, the starting mechanisms you can see is RMS at 120 degrees from each other. The overview of a balanced 3-phase system would show that each of these phases would be at 120 degrees to each other. Moving over then now into our balanced systems. So looking at the questions you were given in the task that was set, we needed to understand what a balanced system would be. So on here, this is a single-phased balanced system. I've taken our each phase that are now 120 degrees apart. And a balanced system basically just means that they are all equal. So the amount of voltage produced in this system is 50 volts per cycle, or per phase. Therefore, it would be classed as perfectly balanced. We've talked as well before, saying that vectors and phasor diagrams can be completed for a number of different purposes. So they can be completed for voltage, they can be completed for resistance, current, and for power. So all the values, if we was to work out current from each of these, as long as the resistance was the same on each phase, the amount of current would be equal as well. So it would be perfectly balanced looking at current, the same for resistance and the same for power. So at the moment, representation of a complete balanced system would be shown from each phase at the same voltage, same resistance, same current or same power, 120 degrees separated from each other. This is a star network. This is what is now installed right across the UK from substations out to all of their commercial or residential situations, because from this point here, they will basically earth their star point, and then we can take single phase to neutral, or we can take two phases, giving us 400 volts, or we could give us all three phases for our three-phase induction motors. What I wanted to show you from here is how, though, that they create delta. So delta, looking at calculation, so when we were looking at the VL is equal to VP times by the square root of 3, I'm basically going to use this 50 volts. And in order to determine, to show you the delta and to use the calculation, delta is the basically connection of all of the star points. So as you can see now, moving over, all I've done on this diagram is now joined our star points. So I have created the triangle of delta, and from that, if we take our 50 volts and we use in the formula, so VP is the voltage in each phase, but VL is the voltage in the lines. So VL is from this line to this line. So between two lines is the total voltage. So using the formula of doing VP times by the square root of 3, so V is what we're looking for. VP, we know that the voltage in each of these phases is 50. Therefore, 50 times by the square root of 3 would give us the 86.6. So again, if you were to scale this out, I have literally drawn these. These are now 5 centimeters, so I've just scaled it down to the 5 centimeter mark. I've done my 120 degree cycle. So if we was to take a ruler, we would actually see that the measurement between these 2 points is in fact 86.6 centimeters. Just give me 1 second. Hopefully you can just make that out there. Sorry. I'm just trying to make sure that you can see that it is possible to do the calculations, but we can also draw this out as long as we have a protractor and as long as we have a ruler. We can actually mark this out and measure it just to make sure that our formulas are working correctly and we understand the process. The two things that we do need to make sure that we can do, however, with these formulas is that we can transpose them, because we might be given the star system to review. However, we might be given the delta system to review through these questions. So here I've basically just transposed it. So rather than now looking for VL, we're looking for VP. So VP, the transposition of this formula is simply to divide the VL over the square root of 3. So the voltage in phase we're looking for, again looking for this voltage. We have been given the voltage in the line, which is between the 2 points. So we take our 86.6 divided by the square root of 3, and we're given 49.96, I think it is. So I hope that makes a little bit more sense at the moment. So we're basically just going to take this star, and we're now going to look at how balanced it is and whether there is any resultants from this. So a neutral resultant is of a higher cost, and the reason for that is that on a three-phase system, and it's perfectly balanced, we are using the entire amount of current within the system at a unity factor. So the power factor doesn't exist. It is a purely resistive circuit. We have no effects within there. So whatever current comes into the system is used, and there is nothing returned at all. If, however, these are unbalanced, so in this phase we decide, or the system is only allowing it to use half of the voltage, we still need to produce the total voltage in phase 1 and phase 2. However, phase 3 isn't using all of it. Because we're having to produce it, in this phase then, we would now have a loss. So the loss would just go directly down the neutral path and be dispersed in ground. Therefore, we still pay for the full production, but we're choosing now to waste whatever's been produced. This is a massive cost to any generation firm. So therefore, they implement a charge. They have a neutral meter that measures the amount of magnetic field returned to ground, and they charge them for roughly about 10 times the cost of production to try and make sure that they use the systems properly, balance the systems properly by monitoring the current in each of the phases, or by putting in power factor correction systems, or by generating their own power through using synchronous and asynchronous machines. What I'm going to do though, hopefully not blow you away too much, is just move you now from the star system and show you how we can actually check to make sure this is balanced. We can see quite clearly from here that the 50 volts in each of the phases, if there was equal amount of currents, if there was equal amount of resistance or power, that they should actually balance out. But I'm just going to quickly show you then on this next sheet. So I've redrawn it out. I've shown you here that we've got 120 degrees. So again, this is representation of a perfectly balanced system. In order to check that it is balanced, what we can do is we can follow a formula. So I'm just going to quickly show you. The formula, again, on these worksheets you can go through and have a look at, is a formula similar to Pythagoras, again, a little bit extended. And what we're wanting to see from this formula here is that everything is balanced. So if we was to follow this system using that formula, the answer to the question would be 0. So there is no resultants, there is nothing outflowing. Again, all I'm going to do now is just show you an easier way to draw this system out and to measure the system. So on here, let's put it into clipboard. If we was to start off with one of our phases, it doesn't matter where we draw it. So start off with one of our phases. We could start here, or we could start around onto this side. Doesn't make any difference whatsoever. What we would firstly do is draw in our phase. So I've drawn this. This is our 5 centimeter phase. What I would then do is extend the phase, and we know that it's 120 degrees offset from each other. So what I would then do is redraw at 120 degrees from this point here to here, my phase 2. Again, we did talk in one of the sessions where we said, why don't you just do the 60 degrees? You can do, but the purpose was to show that we'd extend this line. We would take our 120 degrees and then we would redraw on our second phase. And again, I've just scaled this down to 5 centimeters. What you would then do again is draw your 5 centimeters, but extend this line to show then that our 120 degrees is now offset again. And then I would redraw to scale my phase 3. So my phase 3 again at 5 centimeters representing 50 volts. And we find now, because it is perfectly balanced, it creates our perfect triangle. And again, just to show our 120 degrees on there. So now we have a perfect triangle. So we can see here that these are perfectly connected and there is no resultants whatsoever. There is no gap between this joint. If there is a gap, that means that we do have a resultant force being sent down neutral. So from this image, I'm now just going to try and transfer it over to an unbalanced system to give you a little bit more of an understanding. So the next page is quite busy, so please just bear with me. I will try and go through to make sure that we can grasp any of the information we need to. So from here, I've basically gone back to a star system. So I've now scaled this out to as much as I can. This is a 3-phase. I have written for some reason a single phase on the worksheet. Just completely ignore that. This is a 3-phase unbalanced system. So again, just using voltages on here, what I've done is drawn out my star system. These are all 120 degrees offset from each other. Phase 1 is 70 volts, so I've done this at 70 mil. 30 volts on phase 2, I've drawn out at 30 mil or 3 centimeters, and phase 3 is 50 volts. I've drawn out at 5 centimeters. So we can go through the drawing I just did in this one, where we would do our first phase, draw our line in of our 50 volts, do 120 degrees, do our second phase, 120 degrees, draw our third phase. From this though, we know straight away that it's an unbalanced system, but we need to calculate again how unbalanced this is and what's going on in here. So we can use a nice big formula, or we can use the drawing method. So the second method, rather than without a protractor, as long as this is drawn out for us, we can basically just move some of these lines, and hopefully you can again see from here. All I've actually done now is started off with our phase 1, and I've drawn phase 1 in. What you can then do is literally move phase 2 over and join it to phase 1. I've left on there, you can see all I've done is moved phase 1 and 2 and literally cut it, if you like, from this position, and then moved the end of phase 2 onto the start of phase 1. So I hope that makes a little bit of sense. If we then move over to the next drawing, what I'm then going to do with my phase 3 is I'm actually going to disconnect it from the phase 2, and I'm going to move it down to the end of phase 1. So all I've done is taken this phase, basically cut it and moved it and replaced it down to this section. You're going to have to excuse, I have done on my drawing, I did notice a minute ago, is that the 120 degrees is from here. This cycle should be 180 degrees. This one here is 120 degrees. So just please look at your drawing. Same for there. If we look at that, that is 180 degrees. This one here is 120 degrees. So what I now have is I have a gap because it is an unbalanced system. So if we scale this out, if we draw in our 120 degree cycles, or if we just transfer over each of the phases to the ends of, or the starts of each of the other phases, and I scale it out, what you should actually see is that by scaling this, I can actually now take a ruler and I can measure it out to see an approximation. So if I put an answer down here of 34.5, I wouldn't be far away from the actual result. And this method would be deemed as a good method to use. So again, method 1, I'm using a protractor and measuring all of this out. And then scaling it and to make it easier to understand. Method 2 of just transferring each of the lines and interconnecting them to see any resultant forces and taking a scale measurement from that would be again another good method. But just to prove that this works, I have also then used the formula. So the formula again is the square root of, in the brackets, a squared plus b squared, sorry, plus c squared, minus a times b minus a times c minus c times b. So in the bottom right corner for your worksheet, I again just marked out, so a, b and c at 50, 30 and 70 volts. On the formula again, I've just transferred the correct information, and by putting that into our calculator, we can see then a neutral resultant on this unbalanced system is 34.64 volts. So I hope that this makes a little bit of sense. I've done it on a video lesson, if you like, just so you can see the paperwork and the screens to make sure that you've got something visual to look at. It does try to give you a good understanding from the offset of a single phase system, of transferring it over from a generator to a sinusoidal wave, and then a sinusoidal wave over to a vector diagram, and then from a vector diagram how we can start to mark out and see again our values, so our voltages, our currents and our resistance. I have uploaded onto the classroom page the answer guide to the tasks that we just had out, because a few people were starting to get a little bit confused. The first 2 pages do give you some very good examples, So please use the examples to go through, but then please just look at the answer guide to see how I've actually planned it out. I have tried to give it to make it easier for you to review. From this, though, I will just do a Google Meet. I'll set up a class just for those people that are really struggling for it, but I'll put on a Google form those people who do want to attend, and then I'll get that set up. That will I'll put a date on the classroom for you for that session.